We are recording. Okay. What I want to start with today is talking about some of how program memory gets allocated. And let's see, let's share the screen. Share my screen. Yep, that one. Okay. All right, and hopefully you see a C program with a giant two-dimensional array. Is that true?
Yes.
Okay. Okay then. What I've got here is a program, and I've just got a unsigned char array, which is a bunch of bytes. Got 8 rows, 10 columns in each row, and that's just how you'd set up a two-dimensional array. I made this global, so it's always going to exist within our program. And all I do is I come along here and I set port D to be an output port. And forever I just output each element of my data to port D. And I've got a board here that's not plugged in at the moment, but I could take that board and plug it in and run it. Let me just get rid of my floating meeting controls. Okay. And if I start this without debugging. Oh, okay. I'm not gonna connect an interface, but it would work. Let's just build this and look at what I've got here. If we, let's see, is what I just highlighted big enough for you to see? Or should I put it in?
No, I can see it.
Good.
You can see, okay. All right. You note here that in the allocation, program memory usage is 350 bytes. Data memory usage is 80 bytes. Now, where does that 80 bytes come from? Well, that 80 bytes comes from this 80 bytes right here. So that's 80 bytes worth of data. Let me ask you a question.
Where does it come from again? Sorry.
Oh, okay, where does the 80 bytes of data in RAM comes from? Right here. I've got 80 locations in this array. Each one is 1 byte. And so that's where that 80 bytes comes from. Now, in terms of total RAM usage, would you expect it to use any more, or is 80 bytes just what it should be using?
I would expect with the main program, it would have more bytes in RAM.
Okay, what other bytes are going to get? What other things are going to get stored in the additional bytes?
The integers I and J.
Exactly, that's a good point. Yep. Okay, I and J. Why aren't they allocated a couple of bytes of space? Why isn't it 82 instead of 80? And the answer is because I and J are going to be optimized away. If we look at, okay, and I know we haven't done a lot of looking at list files, but if we look at this list file right here, like expanded output files, click on the LSS file. And we're going to come back to all the stuff I'm skipping over here for a minute. But you can pretty much see here, it is nicely optimized this to just setting the Z register to some stuff, initializing the Z register to the beginning of the array and outputting each thing. It has more or less optimized the variable the variable J into R30 and the variable I into R31. So it's optimized those two variables away by simply storing them in registers all the time. So it doesn't have to allocate space for it. Again, advantages and disadvantages of that is it's going to be faster, take up less space. The disadvantage is if you're debugging it, it gets a little bit hairy, unless you turn optimization off totally. If I go back up to the top here, starting at location 0, what have I got? Right. Got a whole bunch of vectors. Okay, we kind of looked at the vector table in assembly. We looked at it a little bit in C. Location 0, which is the reset vector, jumps to location 104. Just keep that in mind for a minute. Every other vector, it jumps to location 118. So every other vector is location 118. Let's look at 104 and 118. Location 104 is kind of our initialization piece of the C code. We set R0 to 0. I'm sorry, set R1 to 0. R1, by convention in this compiler, R1 is always going to just have the value 0. We output it to 3F, that's the status register. We load into a stack pointer, 8FF, which is the bottom of RAM, and then we call our main program. If we ever come back from that call for some reason, we jump to location 144, which we can skip ahead here in 144, disables interrupts, and just loops here forever. So that's a forever stop. The other piece, somewhere there's a do copy someplace, I hope. There's the vector table. Okay, the bad interrupt. So if I should get an interrupt somehow, it's simply going to be the same as a reset, and I'll jump to location 0. Now, where's do copy? Did I? I literally looked at this 15 minutes ago, folks. There's supposed to be a do copy routine in here someplace. One minute here. Clean solution, build solution. Oh, or okay. File. Okay. I think what I didn't do before is I didn't reload the list file. And I had already made the changes I'm going to show you in just a minute here. Okay, here we go. What just happened is I had made changes that I'm going to show you in a minute, and that had eliminated the do copy stuff. And then I had the old list file when I loaded this. So this do copy is going to take data in program memory and copy it into RAM. Let's go back to our C file for a minute. This unsigned character array, my data, that is going to exist in RAM. Okay, because I come along here and my data is it's a variable. It's going to exist in RAM, and I'm going to output it to port D. But when this is first turned on, RAM is in an uncertain state. So there has to be, this has to be stored in two different places. So it has to be stored in program memory, and then at power up, the contents of this in program memory are copied to RAM, and then the program can happily access it. You have a very limited amount of memory. So if this doesn't have to go into RAM, why bother to put it in RAM? There's no reason to store this data twice if you know it's not going to change. If this is just some kind of a lookup table, for example, say you were doing 7-segment displays and you had a lookup table for the pattern of each digit, there would be no reason to have this in RAM and program memory at the same time. Now, in the first lab you wrote with the 7-segment displays, you put, because I forced you to, you put the lookup table in program memory. And then what instruction did you use to get that data out of program memory? Do you remember what assembly instruction you used?
LPM.
Program memory? Say it again, I think somebody said it.
At LPM.
Yeah, LPM. So LPM goes into program memory, pulls out a byte, pulls out 8 bits worth of data, and puts it into a register. We can do the same sort of thing here. Right, let's look at how we'd make this change. There is
Would you just make it a
program
file
space
variable?
.h file, and if we look at this file, there's a lot of hideous stuff in here, but let's just pick out the things that need to be picked out here. There is what is called a decorator, prog-mem. That says, we have to delve deeper into this, but that says that this data is only going to be stored in program memory. There is also some routines. Okay. That's just the documentation. Let's see. Okay, there we go. There is also some routines called program read byte. And that's again a deal. Let's see. There we go. Okay.
So what does this file actually mean? Like, what does it do? Is this from the board?
This file is part of the AVR environment. And what it's basically going to do is generate code differently so that instead of getting it out of RAM, it's going to get it out of program memory.
Oh, okay.
Let me show you
Generated
the
automatically.
changes you need to make here to this program. And again, it's not important you have a look at that file. I just thought I'd show it to you. But first,
Oh, I see. There it is.
I need to say that, okay, this data is constant. It is not going to change. Now, that in itself isn't enough to put into program memory. That's just going to make the compiler check and see if you do change this, it will flag it as an error if you try to change it within your C code. The other thing I need to do over here is put the keyword prog-mem. Now, personally, in the design of the language, I would much have preferred to put prog-mem over here on the left, but this is the way that it goes. I think that's because it refers to this data as opposed to the variable or something like that. But you need to declare it as a constant, and you need to say that it is going to go into program memory. Coming down here,
Would you do the same thing if you use define? If you just define it?
Okay, define is something different. Define is a symbol. Okay, I understand the question. Let me make sure I can give a good answer here. If I say define X as 2, what that's going to do is anytime it compiles if I do the symbol X within my code, it is going to replace it with 2. If I just had a few values here, I could probably do something like that. But in terms of putting them in like an array or a lookup table, that's probably a little more difficult. And the other piece of this is if I was doing strings, it becomes a little more problematic to do it. So and strings are going to be next. So could I use define for single values? Yeah, and it probably makes a lot of sense to do that. But if I had this was a lookup table, maybe I've got a thermistor that has different values of resistance for different temperatures, and it's not linear. I could put a bunch of different temperatures in here corresponding to different readings. And that's not really something I think I could do with a bunch of symbols. Right, so the next piece of this is I need to modify how I get the data here, because this particular thing is going to look in RAM. I need to say I'm going to look at the address of this, and I'm going to program read byte and surround that with now that is going to generate code that uses an LPM instruction rather than a load Z or something like that. All right, let's compile this. Build solution. And let's reload the list file, which is the problem I think I didn't do the first time. Note now that I have 0 bytes of data memory and 330 bytes of program memory. How many bytes of program memory did I have the first time?
It was 80.
380. So, okay, wait, all right, no, I had, the data memory, it was 80. But does anybody remember how many, okay, so I've gone from 80 to 0. What about program memory?
350?
About 350, yeah, I think it might have been a little bit more, but it was definitely more. So by putting the data permanently in program memory, not only have I saved data memory, I've also saved program memory. Well, let's look at the list file and see what changed. And what changed is, if I've got my vectors, I've got that Ben stuff, I don't have a do copy now. So because the data doesn't have to be copied from program memory to RAM, not only have I saved RAM space with those bytes, but I've also saved program memory space. If I look at this code, okay, right there, lo and behold, is our LPM instruction. So this port D is going to be converted to a few LPMs, or to one LPM and then an out. and then an add immediate word to go to the next location.
Professor, how are you able to get to this kind of file here, which reads out the commands in assembly?
Okay, to get to the list file, let me close this. Okay, what I ended up with was that when I either build it or do a start debug and download or whatever, but building it is enough. If I go to output files, right over here and expand this, one of the output files is an LSS or a list file. And you double click on that, and lo and behold, you've got the equivalent in assembly.
Okay, thank you.
And it,
There it is.
That would have been helpful a while back.
oh, okay,
Yeah, it's having trouble getting it to disassembly.
okay. Okay, there's something to note for future classes there. All right, we can do a program read byte, word, double word if you want a 32-bit quantity, or a float as well. So those are the possible, or some of the possible calls that I can use. All right, questions on that? Now, once again, we've got asked the question, why is this important? Why do I care so much? With the, and I don't think it's going to affect you unless you get really crazy with strings and stuff. But with that parser routine, every time a routine calls itself or it calls a routine which called it, there's a certain amount of stack space that gets used. So there are certain things that are pushed onto the stack and allocated on the stack. There's a stack exists in RAM. There's a limit to how much RAM you've got. It's 2K, it's not a lot. So sometimes being able to save a few bytes or 80 bytes or something like that can make a big difference to whether your program runs at all or not. If you find that your parser routine works, if you do 6 + 2 × 3, but it doesn't work with an expression that's got 15 symbols in it, then it may be you're just running out of stack space. By default, strings go into RAM. They go into both RAM and ROM. For example, let me close this program and open up the one we were looking at last time. Just switch off, yeah. All right. There was a lot of code that can be, let's see, I think I did it in here someplace. Yeah. Right. When we have Space the Final Frontier, these are the voyages of Starship Enterprise, this code is going to be allocated both in program memory and in RAM. Since this is a constant string and it's never going to change, there's not a lot of point in storing it in both RAM and program memory. If we look at the code down here, there is a macro called pstring. That macro says store this, let me uncomment this here. Says code this only in program memory. Okay, that's a piece of this. Up here, once again, a con string too long. This is going to be in RAM. That's going to be in RAM. I can come along here and put a program memory and these strings are now going to go only into program memory. Let's take these out for a minute. And let's just build this and take a look at some baseline stuff. Okay, I'm going to write this down. If we look at program memory usage, it's 2272. Data memory is 174. All right, now, could I make any guesses as to where this 174 comes from? Let's do a little bit of counting up. If I go up to the top here and look through this for possible variables. Okay, well, right there, that transmit buffer, that's 64 bytes of the 174. If I come here, that's going to be, see how big mem buffer, okay. That's going to be some bytes, that's going to be a few bytes. Standard out's a pointer, that's going to be some bytes. These two strings, let's see, that is column 107. We did this once before. 107 minus 40 sounds like 67. Is that right? That's another 67 bytes. This over here is 44 minus 28. Alexa, what's 44 minus 28? 16. Once again, let's look at this. That's 93 minus 17. Alexa, what's 93 minus 17? 76. All right, and I add these up. That's 128 plus 76. Yeah, that's pretty close. Yeah, that up exactly. Yeah, it's just about 174. Okay, so let's make a few changes here and see what happens. I'm going to make this progmem. I'm going to make that progmem. I'm going to make this p string. I think, was that it? Okay. Let's just try to compile or build this and see what changes. All right. Okay. We've gone, program memory has stayed exactly the same, 2272, but my data memory usage has gone from 174 down to 96. Now, if I needed to figure this out and see if I could optimize this anymore, 64 bytes guaranteed are used by this transmit buffer right here. I could make that a little bit smaller. but then you can't put as much stuff into it. So that accounts for 64 bytes. So that leaves me with 32 bytes that I've got to figure out where they come from. Right. These two things are possibilities. That's a possibility. The variable t is a possibility. Almost given. I suppose that could be optimized away to a register. Let's take a look at the list file here. Oops, that's not the list file. Let's click on the list file. All right. Now I still have a copy data here. Yeah, let's keep going through here. Actually, what I can do. Just I'm looking to see if it's easy to see what TXQ takes up. All right, it's not, I thought it was going to be easy to see it, but it's not easy to see it here. All right, so let's go back to the main program here. All right. The M buffer, if I wanted to know how much space that took up, I could go to my header file here. Just happened to my header file. Okay, M buffer is going to take up, well, that's 1 byte. This is a pointer to an 8-bit byte. So pointers on the Windows side take up 4 bytes. Within this processor, how many bytes do they take up? What do you want to make a guess? Well, how many bytes total do I need to access? Nobody. Okay, well, bytes total. In this processor, it goes from 100 to 8FF, or about 2K. In the AVR architecture, I can have up to 64K. So this pointer is going to be 2 bytes. So that's 1, 2, 3, 4, 5, 6. So each of those M buffers is going to take up 6 bytes. Let's go back to the C code. So there's 6 bytes and there's 6 bytes. This file, I need to go and look at it, but that file, I believe, takes up about 16 bytes. And we're now at 28 bytes. So somewhere in there, there's variable t, which is a couple of bytes, and there's probably a couple of bytes I missed.
Is there any way to optimize M buffer, those 12 bytes?
Not without giving up something. I guess that buffer overflow flag, we're not using it, so that could go. But you have to have a head pointer, you have to have a tail pointer. You need to have a pointer to the buffer. size, I suppose you could calculate on the fly each time. You'd lose a little bit of efficiency. So maybe you could take a bite out of it depending on if you're willing to give up efficiency. In terms of the size of the buffer, go back to main. The size of this array, that you could make smaller, but then you don't have as much wiggle room. You have to be a lot more careful with how fast you can send stuff to be transmitted. So I guess my answer is if you were wicked tight on space and you needed to squeeze a few more bytes out of it, then the first thing to probably do is test this. Can you do this? Will this work with 32 bytes? And you'd want to test the heck out of that before you send it into production, I think. Okay, so what should you have gotten from today?
Could you possibly squeeze some more space out of it using the property that structures are defined contiguously to calculate the pointer to the next one on the fly? Procedurally generate memory pointers? I mean, it would be slower.
Procedurally generate, you mean head and tail pointers?
Yeah, like using the property that they're always contiguous.
You'd have to have, if you, for instance, didn't, I think you'd have to have at least one of them. And now we're more into data structures than embedded systems, but you'd have to have at least the head pointer. And
Yeah, but if you
something
preserve
to
the
end
pointer
of
to the head,
queue, you'd have to start at the head and search until you found something like a null. But that would mean that you could never actually put a null in the queue. So what you'd give up is the ability to put in one value in the queue. Yeah, and that may be okay, but I'm not, I mean, maybe you do like 255, since that's not a printable character. You might be able to get away with that.
all right, so it's possible, but not easy.
Well, it's not only a case of it's not easy, it's possible, but there's a sacrifice to be made. In that you're going to have some end of queue character, which then can appear in your data.
Makes sense.
And if you were striving for that last byte, you may want to rethink your algorithm. If one byte's going to make a difference between this program working and not working, you may want to rethink whatever you're doing and just use a bigger processor, because that's awful tight. Years ago at UMass, there was long before we had computers, there were just dedicated terminals. Digital Equipment Corporation came out with a thing of you could plug 4 terminals into this box, and then one wire went back to the mainframe. And this thing was in production, and they had manufactured probably many tens of thousands of them, and UMass, of course, bought a bunch of them. And they found that every so often, one of them would flip out, and they went crazy. UMass was kind of a test bed, and they went crazy trying to figure that out. And it was ultimately a buffer overflow problem. And it was interesting, and it would work for like 3 days, and then it would flip out. So they finally put a logic analyzer on one of these things that was in use and set it to trigger at a certain point, like when it, and over a course of days, actually over a course of weeks, they narrowed down to what it would do when it flipped out. And they'd set a logic analyzer to be constantly monitoring it and then store on a certain event. And they finally figured out it was buffer overflow, and they had to allocate more memory for the buffers. So if you're down to the last byte, you probably want to rethink what you're doing.
All right, thank you.
Okay, in your research, anybody figured out what goes there and that where that null was? And anybody looked at the documentation for FDev stream setup? All right, I'll give you a little hint. Look at the documentation for libc or AVR libc or libc AVR. It's in the lab 7 folder. And when you set up this stream, I'm not going to tell you, but you there will be something here that's going to become kind of useful to you. So I will leave that, but you do want to definitely look at this to make use of it. All right, that's actually all I have today. Any questions?
I have 2 quick questions.
Okay.
So I looked up the FDev setup thing, like you said, right?
Yep.
So, do you want me to say where I put the null and stuff like that? Just like that, I could.
Yeah, go ahead. Go ahead.
Yeah, so I have null, and then I have a variable called key in,
Yeah.
and then I have FDev setup read, right?
Okay.
Actually, key in is a function, I guess.
Right. Yep.
So how they had me do it, and then it inputs file stream, right? But the issue that I was having is it's supposed to go to the key in and then it goes to key in and then it's supposed to be a function that gets the keys from the keyboard. But
Yep.
I can't find anything to read in from the keyboard. I tried to use get character and then I tried to look up some stuff online and on Stack Overflow, but they just kept telling me to use the scanf, but the scanf was what we were trying to change.
Okay. I think you're looking for a function that you need to write. This UART, but on the output side, the UART put character in my code someplace, I had to write that.
Yeah.
You need to write something like a UART get character, which is going to dequeue something and return that. It's going to be slightly different form. You've got to look at the form, but it's slightly different. It's going to dequeue it, and that's what
Okay. Because
it's going to use.
yeah, I was just trying to figure out how I was supposed to get the characters from the actual keyboard and like while writing that function, because I already have a function called key in that serves that same purpose that you were just saying.
Okay.
But I just don't know how to get the input from the keyboard specifically.
Okay. Well, you're not so much getting the input from the keyboard as from the UART. I think you realize that.
No, okay.
Okay. So you're gonna I didn't put it in here, but you're gonna have to create an ISR that triggers when there is a character received.
Okay.
So you're going to have to create a complementary ISR to this one. When the receive flag is triggered, and then you might want to, instead of checking is the queue empty, check is the queue full. If it is, you probably don't want to stuff something in there, but you're going to want to put the character just received, you're going to want to enqueue that character.
Okay.
So
Then your get char, or whatever you call key in, is going to dequeue something and return it to the, well, ultimately to whatever function you put there.
Wait, but do you mind scrolling down again really quick? Let me just.
Yep, sure.
So where is it? Yeah, okay, right there. So, and that one only returns 0 though.
Right, okay. You need to look at And again, the easiest thing for me to do would be to give you the answer to this, but I'm really trying to stretch you because you're going to need to be stretched in 2 and 388. Where are we here? Okay. What the function returns, or how the function returns stuff or takes stuff, you need to look up in that libc document. For the writing, it has certain parameters. For the writing, it has certain parameters. You need to look those up, and those are kind of fixed based on this stream setup. It is true that this put character always returns 0. You need to look at the format for the get character. Does it return the character? Is this a call by address and it returns it here? What's the format for the get character routine? And that's kind of what you need to look at and figure out.
Okay, I see.
So I know I'm being vague, and I'm trying to stretch you in how to read documentation. Because as most of you know, Dr. Weil is far less sympathetic than I am for the most part. And he's the one teaching 388. All right, any other questions?
Yeah, do we still have exams? I know you said we did. Are those coming up soon?
Okay, I thought I said maybe this wasn't 160, I said this. My plan is, there is going to, what did I say here? I didn't tell you guys anything at all?
You may have, honestly, haven't been able to make every lecture. I've been busy, so I might have missed it.
Okay, all right. I will decide that today and let you know on Wednesday. My thought for this course was, the first test is 33%, labs are 33%, and I'm going to give you some sort of a final project, which I guess I really need to give you sort of on Wednesday so you can be working on it. Some sort of a final project. And that final project is going to be 33%.
Jesus. Okay.
So,
Okay, great.
yeah, and so there won't be another test. If you think you would rather have a test, then I guess let me know that before Wednesday. And we'll come up with some kind of a test.
Yeah, I agree with Eric. It would be better to have the final.
We'd better have
Like
a, okay,
project.
all right. We can do that too. I'm A-okay with that.
Oh no, man, I don't test well. So
Okay, I can do some kind of a test. I am, and then so that will obviously be sort of a quote take-home test, and it will be something to write some code on the AVR to do X, Y, or Z. I don't know exactly what yet, but it will be some code to write.
So how's the deliverable for that? Just turn in the code?
The deliverable will be turned in the code. Yep. All right.
Is
Go ahead.
is there gonna be a handout for this lab yet or no?
Yeah, I haven't done a, okay, I will do a handout right now for the lab, but basically it's, you type on the computer keyboard in PuTTY and you get a result back as a, you get an answer back.
It's essentially a calculator, right?
Yeah, it is a calculator. Again, you've got the parse code.
Yeah.
But you're just using, you could take any kind of a dumb terminal and plug it into your AVR. Again, if it's an RS-232 terminal, you need to use the transition chips that we talked about, the MX-232. But you could just type a problem in and get an answer back. And if you, I haven't actually checked the implementation of sine and cosine and square root on the AVR. So if those don't fly, don't worry about that at all. I'm not concerned about that. Okay. So I will write that up in the next few minutes and put that in the Lab 7 folder as well. So there'll be a write-up of the handout, or handout of the write-up.
After this
Okay.
lab is over, we only have one lab section left. Is there going to be a lab for that too?
Is it going to be a what?
After this lab finishes, we only have one lab section left. Is there going to be a lab for that too?
Yeah, because I've got to have, well, I don't have to. It's in your interest to have a lab on both analog reading and analog writing, which is what we're going to start talking about on Wednesday. And I just want you to do a little something with that. So the code will, most of the code I will have given you for the analog reading and analog writing though, but you really need to have seen it. So yeah, there will be one more lab, but it should be a much, this is the most difficult lab you're going to do. The next lab, it will be much easier and maybe even a little bit of fun.
Okay.
All righty. Okay, I will, let's see. I will see you on Wednesday then. Blessings to you. Stay safe.
See ya.